All right. Good afternoon. Thank you for coming. My name's Alan Gates. I'm one of the co-founders of Hortonworks, and wanted to talk this afternoon about doing data warehousing on Hadoop. So let me just start by saying, how is this different than what we've talked about before? All right, let me give you kind of an idea of why I'm talking about data warehousing instead of just SQL. Let me start with a question here. What do you expect in a data warehouse? What do the words data warehouse mean to you when you hear that? To look at what companies in my industry put out, including sometimes my own, you would think that it just means how much of the TPC-DS query set can you run and how fast can you run it. It's a lot of you've seen a lot of if you follow this space, you've seen a lot of blog posts on that. It's what people kind of use for bragging rights, for testing of the completeness of their features and their speed. And don't get me wrong, there's nothing wrong with that. But it's a little bit like just the engine, right? It's important when you go to buy a new car, you look at the engine. You look at, how fast can the engine go, how much horsepower can produce, kind of torque, all sorts of important questions. But that's not the only thing you look at. You go to buy a car, right? Not simply an engine. So let me ask again, what do you expect in a data warehouse? You do want high-performance SQL, and you want it to cover all the SQL you need. Now, I put SQL 2011 on there, not because it has to cover every piece of that, but because it needs to cover every piece you care about, right? It needs to be able to meet your needs, which means that it needs to be fairly advanced in the SQL it covers. But you also want to know that you can store a lot of stuff in it, right? You want high-capacity storage. This is big data, right? Not little data. You need to support all your users. Some people want to do BI. Some people want to do OLAP or Cube. Some people want to do data science. Some people want to do ETL. There's all kinds of things to do in this data warehouse, and you want to support all those. So you need to make sure there's room in your car for all your users effectively. It's got to be secure, right? Do the locks work? Will this keep out the people that need to be kept out? You need to be able to govern it. Can you track what's in there? Can you make sure that people are using it appropriately? Can you understand how things move through it? You need to be able to get data into it. You need to be able to monitor and manage it. And the list goes on and on and on. But you get the idea, right? There's a lot more to a data warehouse than just how fast can you do TPC-DS. So again, I'm not downplaying worrying about how fast you can do TPC-DS, but what I want to bring out in this talk today is that as the Apache ecosystem has matured, as we've seen more and more work go into the big data space, a number of projects come together to form a data warehouse. Now, in a more traditional proprietary world, you would buy one product from one company that did all these things or did all the things that you cared about. In the open source world, it doesn't work so much like that. You tend to have one project focus on one area, another on another. So I want to talk today about some of those projects. Now, I want to be clear, I am being biased in the projects I picked. You could make a different set of choices here and slide in different ones for some of these pieces that I'm going to pick, and I, of course, made the completely unbiased choice to pick all the projects that Hortonworks uses. It seemed like a natural choice to me. But I just want to be clear up front, there are other options. But what I really want to point out is the way open source communities are working together to produce something that can now really start to be a data warehouse and not just a SQL engine. So, having said that, let's talk a little bit about this SQL stuff, high performance, and, about the performance and about the coverage of SQL that you would expect. As I said, I'm going to be biased about which projects I pick, so I picked Apache Hive here. And Hive has been around for a long time. It's, as far as I know, the oldest SQL on Hadoop. But it's changed a lot in its lifetime. It is now able to cover most of the SQL 2011, and in fact, as of the latest release, I believe it can cover all the TPC-DS queries with only minor rewrites here and there. It now has ACID transactions. It has a reasonably advanced cost-based optimizer, a lot of the things you would expect. And it does this at very large scale. These are numbers that we've seen at various users of Hive, the kinds of scales Hive can reach. So it definitely plays well in that big data space. And as you can see, it has or is growing to have much of the SQL you would expect. So everything in green on this, it has, and has had for a while. That kind of pinkish color is newer stuff in the Hive 2 branches, the newest versions of Hive 2. And other way around. The yellow stuff is new in Hive 2, and the pink stuff is also new there, but slightly less new, I guess. And then you can see in the kind of grayish blue there, things that are being worked on now. And so this is what I'm talking about when we're saying we can do SQL 2011 analytics stuff here. It's got most everything you need for that kind of workload. I'm sure you've heard us talk about LLAP by now. This is Hive's work to be able to handle fast queries. So basically, of course, Hive came from a background originally of MapReduce, which is not fast, wasn't built to be fast. It transitioned to using Tez or Spark underneath as an engine, which sped it up, but still in a Hadoop world, if you're spinning up processes every time somebody asks a query, which is the way Hadoop by default works, you're not going to be super fast. So how do you deal with that? You create standing processes that can cache the data, and they are alive and there so that they can answer queries quickly. This is a very common MPP type architecture. But what we didn't want to do is turn Hive completely into an MPP engine. We still want to be able to handle that case where you're going to do a huge query that may take an hour and is going to scan half a terabyte of data. MPP isn't going to tend to do well there because you can't get half a terabyte in your cache, or even if you could, you don't want to blow all your cache on that because you've got other users doing other things, right? So we want it to work in both worlds, so that's why we built LLAP, to enable a hybrid system. For your fast queries, we can do them quickly off this cache, and this is much more than just a cache. We can actually push processing down into it, which is why you see the query executors there. But at the same time, we can still go back and do it old style when we need to. So how do those numbers work out? This is Hive 2 with LLAP versus Hive 1. The big green bars are Hive 1. The little tiny blue bars at the bottom that you can hopefully barely see are Hive 2 with LLAP. And then you can see the bar there shows the average speed up. So, the speed up per query. So anywhere from almost 250x to about 5x speed up there in the time. And notice that number of seconds here is getting down into the 2 to 5 to whatever range. I think the very fastest one on this completes now in around 2 seconds. The interesting thing is, in that query that completes in 2 seconds, it actually takes LLAP about 500 milliseconds to run it, and it takes Hive's planner a second and a half to plan the query. So you can see where we need to go next for our performance work. We're actually to a point where some of these queries we can run faster than we can plan, which I guess is, it's a step in the evolution of speeding things up. So for a long, long time, Hive, of course, has been compared to other projects, other things you can use in the Hadoop space. We get asked all the time, how do you compare against Impala? How do you compare against Presto? These are some numbers we ran internally at Hortonworks on a 10 terabyte data set, again, using TPC-DS. You can see Hive versus Impala here, that basically half of them, Hive is faster, half of them Impala is faster. So this is showing that we're reaching parity with pure MPP type systems, which I think is actually very impressive given where Hive came from and the amount of work that's gone into it. To compare to another system that we see a lot, this is Presto. The small green bars are Hive, the bigger yellow ones are Presto. So on this particular set of queries, Hive did quite a bit better. Now, we didn't just handpick the ones that Hive did better on. The version of Presto we used, I'm not sure it could run all of them. And to be fair to Presto here, part of this is that Hive has some ability to rewrite certain types of predicates that Presto doesn't. And if you hand rewrote these queries, you'd get much closer performance numbers. So Presto can, with a little assistance, reach those same kind of numbers. I'm not trying to say we're always faster than them, but this gives you an idea out of the box of what you get. So you start to see that, the performance. Now, benchmarks tend to be run like you own the whole cluster, you're just running one query, you get all the resources, which, while nice and maybe helpful, is not informative for your real world use case, right? That's not how your system's gonna run when you run it for real. You're gonna have lots of people on there. So a question is, as you add people, as you add concurrent queries, what happens to your runtimes? What do you see? This scatter chart shows you what happens as you start to run 5 queries at a time, 25 queries at a time, and finally 100 at a time. And you can see the averages where they get. So you can also see it starts to spread out a little bit in that average. So you get a little larger standard deviation. But on average, the speed up as you add, or sorry, rather the slowdown as you add more queries is linear with response to how many you're adding. We're not seeing big cliffs or places where all of a sudden your performance falls apart as a result of this. So this is something we're pretty happy with, the fact that you can start to add users and still get consistent results out of your system. All right, so that's the SQL side. The engine is there. What else do you need in this data warehouse to be a real, to be a full data warehouse system? And one of them obviously is high capacity storage. Now, on one level, obviously this has always been there. Hive has always worked on HDFS, right? Which gives you that high capacity storage. But you also want to be able to run in the clouds. A lot of data nowadays is in the cloud. A lot of people are wanting to store their data there. HDFS is fine as a temporary store in the cloud. It's not great as a long-term store because it just from a cost perspective, it's prohibitive, right? You're already paying Amazon or Microsoft or whoever to store it in their object store. You don't want to turn around and pay them to run a computer to keep HDFS up and running. You want to store it in that object store. Now, from a long time ago, Hive, because it sits on Hadoop, which can run on these object stores, works just fine. But it doesn't quite work optimally. Hadoop actually makes an assumption that move is both nearly free and atomic. That's just underlying the way HDFS works, and Hive in a number of places takes advantage of that assumption. That assumption completely breaks actually when you go to the cloud. In most object stores, move is not cheap. It actually turns into a copy. And by definition, copies are not atomic. So that means there's rework to be done to make sure that we can work well in that environment. That when we write data into S3 or WASB or whatever your system is, that we can store that without needing to move it. Because right now, the way it works in Hadoop by default, in Hive by default, is you write data into a temp space until you're done, you say I'm done, a commit happens, and then that's when you actually move into the final space. But again, that doesn't work well in the cloud. So we're doing work in both Hadoop and Hive to make that so you can write into the final location, but still not have that data show up for readers until you've said, yes, I'm done, this is really fully there. And I put the JIRAs up there, you can see how that works. Again, ACID, which Hive supports, depends on move even more than the rest of Hive, so there's work to be done in Hive to get that up and going. And I'd also like to point out that with LLAP, caching becomes even more valuable in the cloud. Caching data in memory obviously is important when you're sitting on HDFS because it's much faster to look it up in memory, but the cost to go back to S3 is much higher than the cost to go back to HDFS if you miss. And so that caching layer becomes even more important. And LLAP is working on adding kind of an anti-caching layer, if you will, or a backing cache in SSD, so that when it does have to flush data out of its memory cache, it can still stick it in the SSDs in case it needs it again and not have to go back to S3, right? Kind of a secondary caching layer, if you will. Now let's talk about a question that doesn't necessarily excite engineers, to be honest, but does excite your bosses and your customers and your users, which is the data secure? If I put my data in here, can only the right people read it or get to it or write it? And there are a number of Apache projects that we put together for this space, Apache Ranger, Atlas, and Nox. I'll talk a little bit about each of those. Security breaks down in at least 4 different dimensions. You might be able to break it more ways. But there's a question of authentication. Are you who you say you are, right? When I come to the system, am I really Alan or am I somebody pretending to be Alan? Apache Nox deals with that. I'll talk about that in a second. Also, obviously, Hadoop for years and years has used Kerberos to handle that. Authorization. Okay, now we know who you are. What are you allowed to do? What rights do you have on the system? What can you read? What can you write? Apache Ranger gives us that, and I'll walk through what that means. There's an auditing question. What did you do? So that we can track that for future reference, especially if there is a break-in. It's nice to know, to be able to track who did what, when. And then finally, there's data protection, keeping data encrypted both on the wire and on disk. And again, that's handled by Ranger in Ranger's KMS in Apache. I'm going to focus more on kind of these middle, or actually on the authorization one, but let me talk just a second about Nox. Nox really, it was given the name Nox as in Fort Knox because it enables you to build walls around your cluster and control how people can get in there. With HTTP and that kind of stuff, it gives you a place to control who can get into the cluster and who can't. Let me talk a little bit more about Ranger and specifically how it interacts with Hive. So Hive itself, of course, offers standard SQL security, grant, revoke on tables, on databases, who's allowed to read this data, who's allowed to write it. But that's about as fine-grained as it goes. It does not, Hive out of the box doesn't offer column level permissions, so you can't say, okay, you can read this table, but not, you can read the employee table, but not the salary column. It also doesn't offer any row level type permissions. By connecting Apache Ranger with Hive, you can get both of these. So you can now say, okay, you can read the employee table, but you can't see the salary, and you can only read the table for rows of employees that report to you. You can't read them for anybody else. Those kind of policies can be set up in Ranger and then exported to Hive. And this is done by Ranger's integration with Hive, where Ranger actually gets a chance to look at the query that's issued and tell Hive yes or no, whether or not you should be able to execute this. But it goes further than that. You want to be able to do more than just say, can you or can't you see this column or row. Sometimes you want to show the row, but you don't want to show all the data. For example, I'm sure you've all had the experience of calling a call center at your bank or whatever, and they say, please confirm the last 4 digits of your social security number, and you rattle off the last 4 digits of your social security number, and they say, oh, it's you. If you're writing the software for that call center, you don't want to show the attendant, or the person on the phone, all 7 digits of that person, or no, there's more than that one, 10 digits of 8 digits of the person's social security number. You want to just show them the last 4, right? You want to mask it. as a complete side note, that's actually really stupid because social security numbers are the first 3 digits are tied to where you're born. And I'll bet everybody in this room within 10 clicks could tell me where I was born. Like, I'm sure Google could tell you that. And so that only leaves you, if you can read the last 4 digits and you can figure out the first 3 digits, you only have to guess 2 digits to break my stuff, which kind of sucks, but that was completely for free and not part of the talk. Just a side note. But anyway, you want to be able to do this kind of masking, right? Where you present something like only the last 4 digits of a social security number, or maybe only the last, anything else like that, where you just want to show star, 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 and then those last 4 digits. Again, Ranger can do this with Hive, and it does this by actually taking that query plan and inserting a function that will do that masking for you based on whether or not you can see that column. Further, there may be policies, security policies, that are based on types of information or where the user is. A very common example of this is personally identifiable information, PII. If you're just an average user of the system, you probably shouldn't be able to see people's credit card numbers. That probably should be reserved for very specific cases. Even people that might be authorized in general to see them probably shouldn't see them except in special circumstances when they explicitly ask. This can be supported. There's also geo-based policies. If you're a user in the US, there may be legal reasons why you can't see European data sets. And so we need to be able to block that out and say, okay, users coming from this geography can't ask this query. Some companies also have time-based policies. Certain queries can only be issued between, say, 8 and 5 during business hours so that employees don't go home and start running unauthorized queries. And finally, there are rules that come about for privacy concerns, like a query can't be run if it would return fewer than X number of rows, because you might be able to figure out who, even though the PII is masked, you might be able to figure out who the actual people are because there's so few rows returned. As an example of that, there are some healthcare rules where if there's fewer than, I don't remember if it's 10 or 100, something like that, people in a zip code with a given condition, and even if their names and addresses are masked out, you can't return the results of that query because it might be too easy to figure that out, right? There's just a few enough people there. This, again, can be done with Apache Ranger and Hive, but it includes Atlas now as well. And why is Atlas in there? Because Atlas does the tagging. It tells you what is PII data, how are these geo-based policies defined, and so you end up putting the 3 of these together to get this. So having talked about Atlas, let me go a little further on that and talk about governance. Now, part of that governance is tagging data, saying what is PII, what isn't, but there's much more to governance than that. And this is, again, is where Apache Atlas comes in. A lot of that is lineage. As data moves through your system, it touches a lot of different things. It might come in through Kafka and run through some kind of storm topology, or maybe you're using Spark streaming or something there. You store it in HDFS, you might modify that data with Hive, and then maybe ship it out to some other database. You want to be able to track those moves. You want to be able to understand where data has come from and going to. You want to be able to look at data flows and understand, if I find out there's something wrong with this data set, who do I need to tell downstream that they have a problem and that they need to rerun their processes? This is what Apache Atlas stores, is the lineage information of this data as it moves through the system. You also want to know what's in there. One of the biggest problems, honestly, in big data systems is what is in my data lake. Knowing what is in there. And this is, again, where Atlas can help you, because it gives you a catalog that users can search and understand stuff. And it gives you a dictionary to define terms. Does everybody in your organization agree on what the word user means? I'll bet they probably don't. I know in companies I worked for, we had a very hard time at times agreeing on what certain terms meant. And being able to define those in one place, tag them in one place, and have one place for users to go and find that information is key. All right, what about support for all your users? There's many things you want to do on these data sets, and I'm not going to even begin to touch on all of them. This one is even more spread thin than other areas I was talking about, but I want to talk a little bit about integration with Spark, with Druid, with AtScale, and with how you can access some of this with Apache Zeppelin. So what is Druid? Druid is an open source project. It's not Apache, but it is an open source project that came about really in the advertising technology world for streaming a lot of data in really quick and being able to do fast queries on the aggregates of that data. We have found it very useful to integrate with Hive to store those aggregates and access them very quickly. If you look at a lot of cubing type operations, slice and dice, traditional OLAP, those types of queries can often be answered very effectively off the type of data that Druid stores. So we've started working on integrating that with Hive so that it can answer those cubing queries well, because that's not something it does super well yet today. Now, in HDP 2.6, which was released a few months ago, this integration is started. It's tech preview. It's not complete yet. In the first pass, you actually have to tell Hive to go ask Druid for the data. So you define what we would call a table in Druid. You assign it a table name in Hive, and then you have to issue a query against that table. That's not the endpoint we want to get to. We want to get to where Hive actually understands the relationship between the table and the index that's been built, and it can figure out and rewrite the queries and say, okay, they asked me for data in this huge table, but I can actually answer that query 10 times faster by going against this Druid index, and so that's what I'll do. And so you can see that picture here where Hive would actually use Druid for those OLAP indexes, and standard tools such as SQL BI tools and MDX and all those things can sit on top of this. Similarly, AtScale, which is a commercial product, now works with Hive to store these OLAP cubes and present them to users through their tools. So this is another way to get that same functionality. And as we integrate Druid, AtScale and other systems like this will just benefit more and more with Hive's ability to answer those very quickly and at very large scales. Now, Spark is a very important tool in the the big data ecosystem, and it's got a lot of great strengths in the way it can do ETL very well. It's very easy for users to get started. It has a great machine learning library. But one of the concerns that we encounter with people using Spark is it doesn't plug well into some of these other tools like Ranger and Atlas. Right? If you need to still keep the security and governance going, and you need to have it in a big shared cluster, that's a little bit harder to do with Spark. So we've worked on building connectors where Spark can actually connect to Hive's LLAP system and pull the data from there. In that way, Hive can use Ranger and Atlas to enforce all your security and governance policies, serve that data out to Spark, and you can still use Spark for all the data science and other things that it's such a great tool for. And this is very important to a lot of our users because that way they can know that their data is still secure, still being governed the way they've set up their policies. All right, let me give you a quick screenshot here of Apache Zeppelin. This is a way you can start to interact with this data. Now, it's great to be able to do all these queries and stuff, but you need a way, how do you connect to this? How do you connect Once you connect Spark, how do you interact with it? Once you connect to Hive, how do you interact? Obviously, we connect with tools, any tool that speaks ODBC or JDBC, but if you just want to sit down and hack around, a very common way to do that these days are the notebooks, like Apache Zeppelin. So this is an example of Zeppelin attached. I think in this case it's running a Spark query. Can also connect it to Hive or anything else. The point is, again, here's an Apache project that fits into this ecosystem to give your users the tools they need. Now, I didn't cover everything. There's plenty more areas that I could go on about, but I only have so much time, and at some point my voice would quit working. So but you get the idea. There's Ambari to do monitoring and management and installation. There's Apache Falcon that does replication and DR and lifecycle management. Scoop that does data ingestion. There are many, many projects coming together to make all this work. So what kind of vision does that land with? This is a slide that I stole from one of our corporate slide decks, but it gives you an idea of where do we see this going. The green is what kind of is Hive's legacy, where it came from, what it has done before. The blue is where we're at now. All that stuff in blue has been released with HTTP 2.6. And then the kind of black on the far right is where do we want this to go? What's our planned next steps here? And so you can see again that we want to grow this into a full data warehousing solution. All right. So if there were things in this that interested you but didn't have enough detail, because I kind of went high level, talked a little bit about everything, you wanted to drill down a little more, there's some talks. Immediately following this one, not in this room, but in somewhere nearby, there's a talk on LLAP, and you can get a lot more of the details instead of just the performance numbers. Tomorrow there's a talk on the Hive Optimizer and how it works, and then on Thursday there's a talk on ACID merge and SQL in Hive, because one of the things that's been added very recently to Hive ACID support is actually being able to do a SQL merge where you load in a bunch of data in a temp table, and then you do in one big pass, you merge all that into an existing table, which is much faster than updating row by row as it comes in. So I encourage you to look at these talks. And with that, I'm done, and I will take questions. Yes? So the question is there a performance hit for security? There is, there's going to be a little bit because Ranger has to look at it, but it's all done internally. So the way both Ranger and Atlas are integrated with Hive, they push the policies into the Hive Server 2, which is the JDBC connection, so that when you need to do that checking, it's local right there. You're not having to go out to some other system and say, can I run this query, which one would be slow and two would be very fragile, because if that system were down, then suddenly you couldn't run any queries. So yeah, there's some small penalty, but it's very minor. Yes?
Hive ACID transactions, does it support updates?
Do Hive ACID transaction supports updates? Yes. Yes, completely supports updates. Supports update, delete, insert, and merge. Yes?
So the subsecond SQL in Hive.
Yes.
2.6.
So the subsecond in 2.6. So like I said, about the fastest I've seen it run, well, okay, so for what query size, right? On the TPC DS with the 10 terabytes data set, I believe the fastest we've seen is about 2 seconds. But again, 500 seconds of that's actual execution, and the other 1.5 is planning time. So it depends on the query. But yeah, that's the range we're getting to in 2.6. Hold on, I got that. Yeah, you. What's that? Can you replace a traditional data warehouse? That depends on your use case. And I mean that 100% honestly. I'm not here to claim that we do everything that a traditional data warehouse does. You need to look at, what this system that I'm talking about, when you put it together, will it do what you need it to do? So the answer is it depends. Yes? Can you do star schema modeling? Yes. We've done a lot of work in the optimizer to make joins work. Now, we don't have a modeling tool if that's what you're asking. But if you build things in a star schema, we will handle that just fine. The TPC DS queries that we're running on are very much a star schema model. Okay, way in the back. Shout. Sorry, I can't hear you. Yes. Mm-hmm. Okay, so the question is why is Ranger doing some of this instead of doing it all in the SQL-based stuff? Hive's approach to pretty much everything has been to try to be as ANSI compliant as we can as we add new things. So when we added the SQL-based auth to Hive, we added ANSI SQL. Now, authorization. Now, I think ANSI does support the column-based read-write controls, and we didn't do that, but that's the only one we stopped short on. Ranger added this initially not just for Hive, but for all of the Hadoop ecosystem, right? It doesn't do any good to secure your data in Hive, but then have somebody run underneath and grab it out of HDFS or something. So the advantage of putting it in a separate project like Ranger is it can coordinate the security for Hive, for HDFS, for any other system that's around there, and you can secure the data all the way around. So could we have added more to Hive? Yes, but partly the Ranger group was already working on that, and we felt like this was the best way to put them together. Yes?
Do you view LLAP as a competitor with Spark?
Do we view LLAP as a competitor with Spark? There's some overlap, but I don't think of them as competitors. In my mind, what Spark is great at is it does really well in a couple spaces. It does really well in the ETL space, and it also does really well in the, I'm a data scientist, I'm going to take this data set and I'm going to play with it this way and that way, and maybe write some SQL code, maybe write some some Scala, maybe some Python or R. Hive would be really bad at that, right? We're not built around the one user playing with a data set. We're built around a whole group sharing a system together. Spark, on the flip side, doesn't do as well at I've got 10 people all using me and they've got different permissions and I've got to share their, I've got to figure out the resource sharing so that they get it all right. Spark tends to assume that you have all the resources on all the machines you're running on and that kind of stuff. So to me, they're really aimed at a little different use cases, even though they overlap a lot, and we both publish the TPC-DS numbers and say how much faster we are than each other. Okay, I think there was one guy over here that kept trying to ask a question, and I kept ignoring him.
It's all about just one question to the transaction support.
Okay.
Do you think it's mature enough to be used in production? In most cases, we use transaction. It means it's mission critical.
Sure.
It has to be mature enough.
So is the transaction support mature enough to use in production? So let me say yes, but let me say a little bit about what we intended the transaction support for. This is not OLTP and it's not high-speed transactions. The transactions we want to be able to support are what we see happening in a data warehouse world, which is things like slow-changing dimensions, or data restatement, or I need to go remove old users from my system because they dropped the service and I'm required by law to remove them, or maybe they've asked me to remove information about them and I'm required to drop it. Those are the kinds of transactions that happen, a few a minute, not 10,000 a second. So Hive is not and has no plans to move toward being an OLTP system where we could support where you would count things in transactions per second. It's about being able to handle those slow changing dimensions and those sorts of things. For that, we do believe it is mature enough. Okay, I'm getting the signal that says I need to get off the stage. So thank you very much, and I'll stick around for more questions if other people have questions.